Hello, everyone. Welcome to the binary episode of the podcast for this week. Before we get into the topics, we do have two housekeeping items to get out of the way first. First, for those of you that didn't catch yesterday's episode, Z has put up a vulnerabilities page on our site. In case you didn't see that before, there you can find summaries for some of the vulnerabilities that we've covered, even going into the past episodes that we had before the break. And there's also some like tags and searching and some nice features like that too. So, if you ever want to refer back to a vulnerability or you want to see one that we've covered and get a quick summary without having to go through the episode, then that is there, and it's a very useful page that you worked on. So, um, just wanted to shout that out. Um, and also, we're going to cover the solution for the Spot the Vuln challenge we had up yesterday and today on the pre-stream. So, the issue, for those who can see the challenge image that we have up of x86 assembly, is the JG instruction for the bounce check. JG is a signed conditional jump. So there's a signedness issue there where passing a negative number for the size can kind of get around that check. It should have been a JA, which is an unsigned conditional. So that's the main issue there. For those curious on the structure of why the assembly is the way it is, I kind of sort of based it on the FreeBSD kernel. You can see that with things like the copy in function that's used. And that's just because at the time I wrote the challenge, it is a bit old. We kind of ported it into the Spot the Vuln format basically. But that was mainly what I was doing research on. That said, it's not completely uh, like compliant with how you would have a FreeBSD syscall, because technically speaking, in a FreeBSD syscall, the RDI argument, like here I use RDI as the user provided arguments. Usually it would be RSI because RDI is the thread pointer, but there's some minor things like that that aren't totally accurate. But the gist of it is the RDI is a pointer to a kernel controlled buffer that holds the user arguments. Um, and the reason I point that out is because someone else pointed out a potential alternate solution, depending on how you want to interpret this. If you interpret RDI as a user controlled pointer, there is a double fetch vulnerability here as well, because it's checked with the comparison and then it's used again in the copy in. Um, but if you think of RDI as a kernel controlled buffer that had the user data copied into it, which is how I intended the challenge to be, then there isn't a double fetch issue. But just like Z's issue last week, you can kind of, if you want to be, uncharitable towards me, or you want to hate me a little bit, then you can interpret the double fetch as an issue too.
I think it's fair, especially if that's operating system level. Like that's usually how it works, where it's moved into the buffer beforehand. I think it's fair not to call it a double fetch.
Yeah. So there's the two potential solutions, but the one for sure, the intended solution was the JG instruction. So yeah. In terms of topics, today we have some NETGEAR issues, speculative type confusion in Spook.js, and a breakdown of Parallels Desktop, where they had a stack clash bug. First, though, before we get into any of those, we're going to talk about the Apple bug bounty program, because there was a post by the Washington Post that covered some statements that have been made about researchers painting the bounty program in a somewhat unfavorable light. And we wanted to talk about this because in the past we've touched on the Apple program a little bit before, and we've hinted that there's been problems with it, but there wasn't really anything concrete that we could point to because of how secretive Apple is with their bounty program, and the involvement of non-disclosure agreements and such, which is actually one of the criticisms from this article. So we'll go through some of the points that are raised by the article and the researchers that are quoted in it, and we'll just quickly cover some of those points and then maybe have a bit of discussion around the conclusion that
Yeah,
the
and I
Washington
guess
Post article makes.
so. Bringing it up kind of on this podcast, on this half of the podcast in particular, just because I feel like a lot of Apple research, or at least when I think about the Apple research, it's the iPhone, iOS targets, because those are some of the big paying both bounties, or if you're going gray market sales, a lot of demand for the iOS exploits. Although the bug bounty does include some of their web app, or potentially include some of the web apps. I believe when Sec and that group of people went after Apple, I think that was last year sometime. officially, like, a lot of things weren't actually in scope, but it was kind of like, well, it would be critical if there was a vuln here, therefore they went for it. It wasn't out of scope, I'll put it that way, which is actually kind of part of the issue with Apple is just the scoping in general.
Yeah. So some of the points raised include researchers who were paid, in their opinion, vastly lower amounts than what the thresholds that Apple outlines are. For example, they offer up to $100,000 for exploits to gain unauthorized access to sensitive data. And they outline that as access to like contacts, mail, messages, photos, that kind of thing. And one researcher by the name of Cedric Owens reported a bug that gave access to victim files, though not specifically the outlined areas on macOS, which could still be valuable for attacking corporate networks or just other types of sensitive data that aren't in the messages. And he was paid $5,000 for that. So you could argue that he wouldn't be eligible for the full amount because he wasn't hitting the exact scope that they pointed out, but 5,000 still seems pretty
That's
damn
quite a
low.
drop, yeah,
Yeah.
on it. Like to drop from 100,000 as a max. I mean, I guess that is worth saying. Like that is up to $100,000. So if the vulnerability itself was for whatever reason not qualifying for a max payout, that can also to some extent pay or explain it. Uh, I'm sure we could probably find the details on exactly what this vulnerability was, although I did not when preparing the show notes here. Although they do also raise one other case where Nicholas Bruner had found a bug. It was intended, for helping blind people navigate the train system. He was working for Swiss Federal Railways, and he found that even if users didn't share their location, he could still see their every move. And was expecting like a $50,000 bounty for it. And Apple decided that the bug didn't qualify. And this one in particular stood out to me just because it sounds like it's a type of bug where there's probably something really simple, really stupid that Apple did. Um, and they just kind of decided, like, no, they're expecting like these bug bounties to be these crazy chains, really cool exploits or something. And they're just like, no, you didn't do this one thing. So, like, this really stupid issue happened. They're like, well, we don't want to pay for that. Again, I don't know the details. It just, the way it went from $50,000 down to none, and they decide the bug didn't qualify rather than being like out of scope or something. The way it's phrased there, it feels like that's the sort of issue to me, especially when this guy wasn't bug hunting. It just noticed this thing when he was working on a normal application. Um, yeah, it doesn't set a good tone for all of Apple's bug bounties. I will say Apple does get a chance to defend themselves here. They do mention that their program has been a quote runaway success, and Apple has nearly doubled the amount it's paid in bug bounties this year compared to last. I feel like that's kind of cheating because they own last year was the first full year of the program being public at all. So like to say it's doubled is yeah, people found out about it. It's I don't know. It just rubs me the wrong way, I guess.
It's definitely a PR spin.
Yeah. Which is
Um,
fair. I mean, you've got to expect their PR to do that spin.
yeah. And then even in other cases where they did pay, it was stated that they take a lot longer than other companies like Google and Microsoft to pay out. I think that was stated by Sam Curry, who some of you might know by name, but yeah, he submitted bugs. Him and a group of people submitted bugs to the Apple Bounty Program, and they got about 500,000 total for their findings. So they did get paid, but it was late. Um, there was also other various researchers criticizing the closed source nature of the reports and how secretive Apple are. Along that line, sometimes researchers report bugs and Apple just doesn't get back to you and doesn't fix it for months. This happened to Tian Zhang, who also submitted another bug to Apple, where Apple said that it was eligible for a reward, and his reward was apparently being kicked out of the Apple Developer Program. They didn't actually pay him anything if he's to be believed there. So uh, there's some weird stuff that's covered in this article that
Yeah, and
that
that
is
last one
questionable.
the last one feels a little bit like we just don't have all the information. I mean, granted, Washington Post, we're not going to have all the information.
But the
But
Washington Post also is a fairly reputable source. Like, I kind of would expect the statements in here to be true.
oh, well, it's not so being true and having all the information are different scenarios, though. I just mean like we're hearing his side on he got kicked out after reporting ability, but we don't have any indication of why Apple did so. It does like something's missing there. Maybe it was Apple still acting in bad faith. I'm not necessarily saying anything about that, but it's difficult to really read into that with just these comments.
That's fair to point out. Um, yeah, I would agree with that.
Yeah, and
Um,
Dilbert Marker out of chat also mentions, Apple also know the total amount paid, which is actually somewhere I noticed Washington Post here was kind of at least a little bit suspicious in how they handled that. They talked about their competitors in one paragraph. Specifically, they call Facebook one of their competitors, and then they're talking about how much each program pays out. Yeah, so up here they talk about how like Facebook, Microsoft, Google, they publicize their programs, they highlight security researchers, highlight certain bugs, and kind of make it like you participate in the bug bounty and you can get some publicity out of it. Apple, as far as I know, doesn't really do that at all. So they mention like Facebook being one of their competitors, and then the next paragraph here when they're talking about how much everybody else pays out, they mention Microsoft paying out 13.6 million, Google paying out 6.7, Apple paying out 3.7, and they just don't mention Facebook, who happened to pay out less than Apple at 1.9. And Apple had paid out uh 3.7 million. So I thought it was a little bit weird that they decided to drop Facebook. It goes with their narrative though.
I will
Uh
say I don't necessarily know if comparing how much they've paid out in total over a 12-month period is really a good metric to look
it's
at
not.
anyways.
No,
It just
it's
doesn't really
not.
tell you anything. So,
Because like Microsoft, they have so many products and there's several that they pay out quite well for. There's such a huge, I mean, I guess Apple is a huge company too, market value especially. It's not like they don't have the money,
but
but
they
their
they don't have as
programs
many
are
product
different.
lines.
Yeah.
Yeah. Um, yeah, just looking at how much a company is paid out just doesn't really tell you anything. So I'm not really sure why they had that in the article. Um, anyway, toward the conclusion, they argue that all of these stories and what has happened in the Apple Bounty program and how closed off it is has pushed more exploits to gray market rather than being reported to Apple. Um, and what I think the main annoyance is from various researchers who posted in here was just that when you compare Apple's program compared to competitors like Google, Microsoft, not just on payout, like I'm just kind of ignoring that total payout thing, but just how they act in the bounty program and how much more accessible it is, that Apple really falls short when you compare them to those other companies. And it is a bit strange because they are a leader in security in other areas. Like their mitigation game is really strong. Their sandboxing is good. Um, they kind of pioneered a lot of mobile security. But it seems on the bounty side of things, they just really don't want to play ball with how other companies are doing it. Um, so
Which is
it is a little bit
unfortunate.
strange.
Especially on the just research device side and how difficult it is to actually get in on that program. Because like, sure they allow testing of their devices, they allow testing of iOS, but they make it hard to actually do that testing if somebody were interested in it.
Yeah, you basically have to sign up to their developer program and apply for a developer device.
And
Um,
as I understand it, not a lot of people actually get the devices from that.
Last I remember, yeah, it's really hard to get accepted into that. And that's why companies like Corellium have been established, right?
Yeah, and
Um,
then I think maybe I should have looked this up, but I think you also lose out on some, if not all, of the bounties if you use their devices for search. Like you're still expected to
Ooh, that would be
report it over
crazy. I
to
don't
them,
remember
but
seeing that,
yeah,
but
that's why I'm definitely going to say that is something I'm running off memory with, and not something I want to go on record as saying like Apple definitely does that. I want to go look it back up. But I do remember there
Yeah.
being at least some downsides to using their devices.
I'll put it this way: it wouldn't surprise me with how Apple is.
Yeah.
Um, but yeah, I mean, one thing I kind of wanted to touch on is their main conclusion here is that this drives more exploits to gray market. Um, do you think it's fair to put blame on Apple for that with their bounty program, saying that
For the most
it's forcing
part,
more exploits through other channels?
I would lean towards no. I feel like the people that are willing to go to the gray market and just sell their exploits are already going to be doing so. It pays better. Like they're going to have the motivations. They're not going to be like, well, Apple doesn't want it, therefore I go that route. I'd see more people going, therefore, public disclosure, if they're not the type that's going to want to sell in the first place. That said, I mean, I'm sure there are some people, like I could imagine somebody who was expecting the bounty got kicked out of the program instead. Uh, like the one fellow we were mentioning earlier. I could absolutely see that being a case where they'd go and be like, well, let's see what I can get on the gray market. Although they've already disclosed to Apple, they can't sell that particular issue anymore. But in the future, I could see it pushing more people away from Apple rather than to continuing Apple but going gray market. I feel like, the people that are willing to go gray market would have already been willing to go that route. And I have to imagine the number that would just go elsewhere versus gray market um, is fairly small. That said, that's me making an educated guess from my own background. I have no stats to back that up.
I mean, I was kind of thinking along the same lines, where there might be a few people that would submit to the bounty program if it was more accessible instead of selling to gray market. Um, but I think they're making it sound more more of an issue than it is. Like they're making it sound like almost everybody who sells to gray market would suddenly start selling to Apple if their program is better. And I just don't really think that's true necessarily. Um, but I guess it is a fair argument to bring up that if their bounty program was a bit more accessible, was a bit more friendly, um, overall it is a net benefit for their user security. I don't think there's any doubting that. So I think it's fair to criticize Apple here. I just found some of their points to be, yeah, I think some of their conclusions were a little bit hyperbolic with how much they're saying that it's pushing exploits to gray market.
Yeah,
So
but it's interesting that it's being covered by Washington Post, mainstream media here in this case. It's not just us ranting about some bad bounty programs on the podcast every so often, but other people are noticing the same thing.
yeah, that's the main reason I wanted to bring it up. It's just so that we have something from a reputable site, at least when it comes to like tech reporting, that we can point to and say, here's some stuff that's happened with this program. So, yeah, but not too much more to add on to there. Just wanted to talk a little bit about the conclusions. All right, so we can now move into the vulnerabilities of today. We had some NETGEAR stuff yesterday in the form of a broken access control in the NETGEAR D7000, and we have NETGEAR returning today in three vulnerabilities posted by Guy and Vol in smart switches.
Three
Um,
named vulnerabilities, very
yes,
epic
we do have to
names.
point that out. Yeah, we've got very scary names in here, like Demon's Cries and Draconian Fear. It's very,
Yeah,
you
I
know,
almost feel like these names were just done for fun. I mean,
I
he's
think
obviously
so
not
too.
pushing them out with any sense of real, like, take my name vulnerability seriously, guys. They're very
They're
cool names though. Yeah, you already sounds, but yeah.
not making a website for it and putting like a big logo there, just kind
Yeah,
of
three
through the
websites.
article.
But
Yeah,
honestly, so the vulnerable, especially the last one we're going to cover, is it Seventh Inferno, had
yeah,
a really cool chain, but they're also just really stupid issues.
yeah. So the issues are somewhat higher level issues. They are like binary based, but they're not like memory corruption or something like that. Um, but
Fortunately,
yeah. The first issue is probably the simplest one. It's in the Smart Control Center daemon, and it is again kind of just a bad authentication issue. The daemon can act in one of two modes, being disabled, where it'll only reply to basic queries, or enabled, where it allows configuration to be changed, uploading of with like uploading of firmware images. There's some other features in there too. And the administration tools that work with that daemon suggest that any set type commands require password authentication, which have to come first in the tag length value chain, which is the TLV10 code. But the daemon doesn't actually enforce that. So if you use like custom tooling that interacts with the daemon or whatever, you can just use these capabilities without entering a
Without,
password.
yeah, without sending credentials, which, I mean, it's great. Authentication optional. Who needs it?
Yeah, very good.
Straightforward though. I mean, it's just the standard that you send your password with these requests. It's not requirement.
Yeah.
And that's basically all you really need to know about. They do talk about a couple other bugs, like the fact that there can be a denial of service if your password happens to match with a X or a key width when you do a password change. Um, and there are some other bugs covered in the actual reports. I think the other two each have some that I'm not sure we'll actually cover because it's not the main issue.
Well, I was gonna cover one of them because I did say earlier that there's no memory corruption, and I guess I kind of lied on that because they did point out another issue where the auth handler itself that they should be requiring for TLV10 will take a password even in disabled mode, and it'll copy that into a 65-byte stack buffer, but there's no checking done on that length. So there is a stack overflow there. The problem is because of how the stack is laid out plus the fact that there's stack canaries means that this probably wouldn't be exploitable. Um, like even if you had a leak and you could leak like the stack cookie, if the stack layout leads to something crashing before you can do something useful, then yeah, it still might not be exploitable there. So I just wanted to point out that out because there is some memory corruption issues there. They just didn't really find them to be useful, unfortunately, due to the exploit scenario. Um, but yeah, like you said, there's a few different issues that are pointed out in there. The XOR one I thought was pretty funny. That's just a really weird problem. But yeah, that's all there was for that issue. We'll move into the next issue, which is the second name vulnerability, also in the authentication flow, but perhaps a little bit more interesting in terms of how the attack works. Um, although it's less impactful than the first issue because it requires the attacker to be using the same IP as the victim. So it'd be kind of a specific scenario where you'd be
Same
able to take
IP,
advantage of this.
yes, but I mean that could be. Well, I was going to uh give the case of perhaps JavaScript running on in the browser, but you've got to time it very well with the login within a second. Um, yeah, I mean, I guess it's not that impactful, but it is still a interesting issue nonetheless, where you kind of hijack the authentication process. And in this case, like the gist of how the whole login process works is you send your credentials in like a normal login. The application writes your user, your password, and a few other pieces of information like your client IP, and it buckets your user agent into 5 values or indicates if it's like HTTP, HTTPS. Just write some extra information out to a file, and that's kind of new line separated. Writes it out to a file and then signals another program. That other program will then process that file, and one of the values in that file is where to write the results file. So that other program reads the file, sees where to write the results, and then will write like a successful login or whatever over to that file, or unsuccessful, but we're assuming success. Writes that over, and then in the meantime, after they've submitted that login request, the client is just going to every second pull this get CGI page, and that one's just going to keep checking until there's something written to that results file. The thing is, the get CGI, it only determines what results file to go look at based on that client IP and that user agent string. Those are the only unique piece of information. So if you had somebody else, same client IP, could figure out the user agent or spoof it, set up whatever you want, close enough to match. As long as you set close enough, you'll match. And then if you make the request before the original browser does, you'll get their session. So you kind of take over the authentication process.
Yeah, it's kind of like a race condition with how the
Bit of a
attacker
race,
can.
yeah.
how they can beat the victim to
I
get
mean,
that session
a
information.
very easy race if you know what's going on, at least, because you do have an entire second between requests.
Yeah, but yeah, very large race window.
Yeah.
Um, the suggested fix for that was just to use like cryptographically secure random file names for the results files, so somebody else can't just guess where that information will be.
Yeah, use that, send in a cookie. I know they didn't mention cookies in particular, but that would be an easy way to pass that sort of value back to the browser and have it replay it for you.
Yeah. Um, our final issue for Netgear, I believe, is kind of based on that same authentication flow, but it's a slightly different issue when it comes to new line injection through the password field, which on its own might not be too useful when it's combined with some other bugs like a reboot DOS and a post auth shell injection. It can be used to get root code execution.
Yeah, so
Um,
with this one, like the chain is awesome. I mean, just as a bug, as a proof of concept, it's a great chain for the attack.
for sure.
Um, and I kind of hinted towards this, but yeah, the authentication process, it writes out to that file in a new line separate way. So username, new line, password, new line, file to write results to, new line, HTTP, and whatever else comes after, but new line separated. But they don't check if that username or password you sent in contains a new line. So you can go ahead and just inject your own new line, get that in there, and then take over and provide other values for everything else. In particular, that value that's going to write the results to. It gives you a primitive for effectively a arbitrary file write, but uncontrolled data. So you can control where it's being written, just not what the data is. It either writes a 2 for a failed authentication or a 3 for too many login attempts that have failed. So you can basically write 2 or 3 to any file on the system, which initially, doesn't seem too powerful. They were able to chain this in a couple of unique ways. Well, actually, not that unique. Overwriting the session file being one of them, and then for the denial of service later, which helps get code execution. Covering them in better order than that. The some or how the session authentication works. So once you went to log in, it would if you wrote a file that just contained 2, that would be processed as though it were a valid session file. So what he found was literally just that file is an okay session. That had several bugs kind of leading to it. One of them being they didn't check. So with every request going in, once you're authenticated, you're expected to send this xcsurf XSID header, and that gets decrypted using their own RSA key and gets stored in this G session ID variable. That is then used as part of the file name for the actual session, which is fairly standard. Somewhere in temp sessions are sitting there, login underscore HTTP or HTTPS underscore that session ID, find the session file. So they send that in, or they decrypt that value, sorry, so the user doesn't have direct control over it. But what happens is they don't check if the decryption actually works. So if the decryption fails, gsesh ID just stays as a blank value, but they don't have any warning, so they can kind of know what session ID is going to get used or what session ID file will be used. That's how they knew where to target the login HTTP file with, or sorry, the session file with writing that to a file. And then when it's actually parsing that, it expects some more new line data. 2 obviously isn't new line separated data, but it just uses fscanf to read any of that. And the problem there is it doesn't check if fscanf actually succeeded and read very much data or how much data it read. They don't look the return value there either. So just writing 2 is a valid session file. And you just need to have it valid. There's no user levels to be concerned about here. The only problem is that session value, when it is parsing them, it's going to be parsing them into other values. Those are going to keep their initial values, which for the session creation time will be 0, which ends up being too long and the session gets rejected because it's like, hey, this is a really old session. we don't want them to actually log in with this one. Um, and in kind of another odd step, their session creation time is just based on seconds since the last reboot, rather than, more standard Unix timestamp being from 1970. So just seconds from last reboot. So that's where the reboot denial of service attack comes into play. By being able to reboot the server or being able to reboot the device, they can then have that 0 session creation time as a valid session creation time. And the vulnerability here, they just wrote off to the proxys or your syscontrol files or panic on or panic on out of memory, panic and panic on oops, right to those files, enabling them um so it'll crash when the device runs out of memory, which they happen to be able to do just by uploading any file to the device, any large file to the device, because file uploads are backed by RAM. So at that point, reboot, the session's acceptable, and you're in with uh basically with full access to the device. You could replace the firmware at that point. They do mention a code execution or code injection vulnerability in setCGI's diag trace route. Host name can literally just inject into what backticks in your code or whatever you want. You can do that. He calls out, though, the fact that they can replace the firmware as a legitimate admin is, having code execution isn't the biggest deal. It's not some huge vulnerability because they already have equivalent functionality legitimately. But this one in particular could be called. So all of these things so far in the chain could be done from just malicious JavaScript on some random page, making these requests out. Now, that is a statement out of here that they can definitely be done that way. I am wondering about how it deals with pre-flight, or if this will respond to all of the head requests or options requests, allowing it, or what's going on there. Because I would have imagined that for any sort of... Actually, I guess that does rely on being post. If all of this can be done with get. Yeah, I don't... So one of these, the code execution has post data. Yeah, post should give, I would imagine, should get blocked by just the browser pre-flighting that request and seeing if it's allowed. The gets will go through, you just can't read the response. So I'm assuming you must be able to do all this over get. I don't know
Yeah,
if
it sucks they
that's...
didn't have the requests there for you to be able to take a look.
Yeah, I
Because
mean,
I took a quick look too and I didn't see any.
on a whole, this was a really well-written report. I didn't feel like there's a lot of cruft in here. Got straight to the point, had background, but the background was necessary to understand. It was a well done report. He mentioned specifically that you can do this with JavaScript, so I'm thinking about that other issue, but I can defer to his judgment there and say you can do this with JavaScript.
Yeah. Overall, I mean, a very cool chain to be able to craft a fake session like that. Um, it's it's a chain that I don't think I can even think of a topic we covered before that has a similar attack flow or exploit strategy. Just because it's so dependent on the weird way their authentication works. So it's a very targeted bug in the way that it works, and it's a lot of bugs too. Like the main issue is the new line injection, but it's also all these failed error checks where they just don't check anything. There's probably 6 or 7 bugs or something, just in the way that they took advantage of this exploit. Where if any of those was done correctly, it might have foiled this from happening. I think that's probably the most cool part of it.
Yeah.
Um, but yeah, out of the three, Seventh Inferno is definitely has the most interesting attack strategy. Even though the original issue is relatively straightforward. All right, so speculative execution is back in the news cycle with the announcement of Spook.js, which targets Chrome. It can target other browsers, but they don't demonstrate that. I think they're leaving that for future work. But yeah, targets Chrome and its defenses against previous speculative execution attacks like Spectre. mitigations like strict site isolation are the main ones that they tackle there. It can be used to see what other sites are being browsed, retrieve information from those pages as far as login credentials from autofill, and retrieve information from Chrome extensions like password managers if they install a malicious extension that abuses the issue. Before we go too in depth on the paper, I do want to touch on like what exactly speculative execution entails for those of you who maybe aren't too familiar with it. For those who aren't too familiar with it, it's based on the fact where modern microprocessors will try to optimize and predict what code will need to be executed through branch prediction, and it'll execute that before it's actually needed to prevent stalling on waiting for those instructions to complete. Now, obviously, that's not perfect, but if it guesses incorrectly, which happens very rarely, it can just execute the instructions on the proper branch and reload the information. So it's a very useful optimization for the processor to have, but it opens up this side channel that can be taken advantage of. Because if you can intentionally train the branch predictor to take a particular route, and then force it to take that route when it shouldn't, you can get information loaded into the cache that can remain through further execution, which an attacker could take advantage of. So one of the things browsers like Chrome did after that mess of speculative execution attacks came out was they enforced strict site isolation, which does a few things, but primarily it separates different sites and tabs into different processes. Now, Spook.js, one of the things it does is it takes advantage of a few different tricks to consolidate sites into the same process. For example, if you have an XSS or something in a target website and embed an iframe containing a different page in that same domain, those could get consolidated. Another strategy is if you can apply a lot of memory pressure to Chrome, it'll try to consolidate sites in different tabs with the same site in the garbage collection process.
And I will
But
say, I don't really feel like there's strict site isolation bypass here, because they basically just do that by saying, like, yeah, you can launch this attack on a subdomain, as it will consolidate the subdomains together. I feel like that's almost more of an accepted risk of how they chose to implement it, rather than a real bypass.
yeah, you still do have to be on the same domain. So in order to take advantage of this, you would need like an XSS or something. It would be kind of a specific attack. Um, and that is one thing I want to get into a little bit later is like this this attack is cool, but I don't think it's super practical. But we'll cover the attack what the attack is first. So yeah, they take advantage of those tricks to consolidate tabs into the same process. Once they have that consolidation, they demonstrate an attack utilizing speculative type confusion to obtain an arbitrary read in the 64-bit address space, and that's to get around Chrome's 32-bit heap sandboxing. Because another thing that Chrome does is it has sandboxed heaps where a heap only sees 32-bit addresses, but then on the back end, internally in the engine, those addresses get added to like a global pointer to access the real addresses, so to speak. Um, so their goal here is to get a malicious object that they control the properties of to get confused for a uint8 array. And in that way, they can gain control over the full 64 bits of a backing store pointer of uint8 array, and they can use that to get an arbitrary read. I'm not going to go too much into that. It relies on some of the browser internals and how things like uint8 arrays work in the JS engine. They do have like some diagrams that show the object layout and memory, but basically all you need to know for understanding the attack is that um, the uint8 array will have a backing store pointer, and you can control that with this attack.
Yeah, and I
Um,
mean, the interesting thing here on this attack, I think, is the fact that they kind of go for a type confusion in the speculation only. So, like, their actual code wouldn't be vulnerable to any sort of type confusion attack. But they end up tricking the CPU into speculating down a path. So they train it a bunch of times. I think it's like 10,000 times on, like, yeah, we're going to access this U8 array. We're going to access that every time, every time, every time. And then they go and swap out the argument at the end and swap it out with, okay, actually, it's this attacker buffer, and this if statement's going to fail, but the branch predictor is going to think it'll succeed. So the whole speculation all of that ends up happening while this branch predictor, yeah, Spectre just brought it up here, where if array index less than mal object f0, then it goes into the actual access. So when they change it out on the actual attack, all of that happens out under this if statement. So Chrome was never aware that this mistake ever happened, that this type was changed, which was one of the things they had to avoid, was Chrome seeing, oh, the type of this has changed, therefore they'll de-optimize the code or swap it out with something else for that particular access. So I thought that was really interesting, just using that and having a fairly lengthy set of code that needs to run under pure speculation, that needs to run when that branch gets miscalculated, which is one of the other aspects they had to go at with this attack. Usually, we talk about kind of with Spectre attacks, you're getting about 10 cycles under speculation, which was sufficient for getting some loads to happen, but they have quite a few things here that they want to get done. So what ends up happening, or what they end up needing to do to get get the predictor to basically keep running longer before it knows that the prediction was actually wrong, was instead of just evicting something from the cache like you would do with Spectre, they had to evict it from L1, L2, and L3 caches. Or basically, they had to evict it from all the caches, all the local caches. So it had to do a memory fetch, which was one of the challenges to this whole thing. It's where this could, in theory, impact AMD. They just couldn't find a good way to evict anything on demand from the last level cache. But if they had some primitive that could do that, then this would have impacted AMD, or could impact AMD also. The issues there, it'll speculate over it, but they just lack that one primitive. So I thought that was really cool that they went for the type confusion out of it, out of the
Um,
speculation.
just to confirm there, I didn't think it was memory accesses, but I thought it was from the last level cache. Um,
Well,
oh,
so
right.
they
Okay.
evict
Sorry.
from
So
the
it gets
last level
evicted.
cache. So
Right.
the CPU, when it, in order for it to know which path to take, it has to go hit RAM. So it can't just go to L1. Like, if you only evict from L1 cache, it'll fetch that from L2 cache. So that takes another like 10 milliseconds, or 10 cycles. Sorry, 10 milliseconds would be quite long.
That'd be a
It
long
takes
time.
yeah, takes about 10 cycles. Is the number they mention here. Similar deal if it's not an L2, another 10 cycles for L3. But it'll take about another 100 cycles if it has to hit RAM. So that's where they evict it from L3 cache, or from the last level cache, so that it has to go all the way to RAM. That gives them about 100 cycle period during which they could speculate on more code, or get more code executed under speculation.
Yeah. Sorry. So I was just, for those reading or sorry, for those listening who can't read what I put up on screen here. I was just confirming that with the statement here when they say when the field is evicted from the last level cache, it is retrieved from the main memory, taking over 100 cycles. Okay. So yeah, that kind of um, helped me understand what you're saying there a little bit more. But yeah, so like you were saying, they needed that speculation window to be long. And that was their main limiting factor on compatibility, is that they had to force evictions in the last level cache in order for the attack to work. And they couldn't find a gadget to perform last level cache eviction on AMD. So as it stands, this only works in practice against Intel chips and Apple M1. They did do some testing just to see how well it would work against AMD. And the way they did that was they made the browser intentionally expose the CL flush instruction. But that is something that you can't get on like a production build. They intentionally modified that to expose that instruction just to see how it would work.
I kind of
Um,
wonder why AMD's a little bit trickier on this. Like, I just don't know about the CPU design level here, so I'm not sure what they're doing exactly. But I am kind of curious as to why AMD doesn't have a somewhat reliable primitive for getting something out. Like, I mean, obviously you can't just make the request in general, but usually it's somewhat deterministic, like oldest or least recently used, or something along those lines. So it is a little bit surprising that they couldn't find a primitive that would work reliably here.
yeah. there was some other obstacles that they had to get around. For example, the way that the eviction works is in order to cause the type confusion, they need the cache line that contains the type to get evicted. But in order to get control over the pointer, they need that data to stay in the cache. And what I thought was kind of cool here was how they get around that is they leverage garbage collection to compact objects in memory in a way where your malicious object wouldn't fill an entire cache line. So it basically gets compacted. Um, and that way you can always ensure that you'll get at least one object that kind of spans across two different cache lines. That
Yeah,
way one
so
could get evicted and the other one would stay in.
yeah, so they would create like a bunch of them in order for a large array to get compacted down, they're saying. And then at least one would end up straddling that boundary between two cache lines.
Yeah. On a side note, being it like the garbage collector is such a useful thing as an attacker against the browser, which is kind of funny because the whole idea of a garbage collector is to make memory management easier, try to prevent attackers from being able to get memory corruption in the first place. But you'll notice like a lot of vulnerabilities in the browser or a lot of exploits intentionally induce memory pressure in order to force the garbage collector to run. And it's just funny to see how useful it can be in situations like this. Um,
Yeah, I think it just removes some of the entropy in general. Is kind of
yeah,
the benefit of running any like running after the memory after the garbage collector, because it can be a little bit more stable, know a little bit more what's happened, because in theory, if especially if you're forcing it to run, you're in a low memory situation. It doesn't have as much room to mess with you, basically.
yeah. Now the paper does go into a lot more detail on how the like eviction gadgets and all that kind of stuff works. We're not gonna cover that here because we would be here forever if we tried to go into that. And
It's a bit
to be
beyond
honest,
me.
yeah, it's very technically complex because you're talking about the microprocessor here. Um, but yeah, I mean, technically, this attack is pretty cool and employs some neat tricks. But I was saying earlier that I would get to the practicality aspect, and I don't think this is practical. The attack is very slow. When you get to the evaluation section, you'll notice you're talking a leakage rate of around 500 bytes per second on most of the processors they tested against. They tested against like 6700K, 9900K, just various processors. Yeah, pretty much all of them were around 4 to 500 bytes per second. Um, you also have no prior knowledge of the memory state before going into this attack. It's not like you have a WebKit or like a browser bug that lets you get an info leak. So you're probably going to need to scan memory as an attacker to find information that you want. And you're talking about a 64-bit address space. That's going to take a really long time. That's over 500 hours per gigabyte in memory to leak, which is just not really feasible. They did show some examples in the paper of how they exfiltrated cookies and other stuff using Spook.js. Unfortunately, I couldn't find anywhere that they go into detail on how they get a starting point of where to actually leak from. So my assumption is they used a debugger to find where the object was and perform the leak, which is valid. They're demonstrating they're able to leak memory, but that's not practical with that leakage rate. You're not going to be able to scan memory with this very easily, as far as I can tell. So it's a cool attack. I don't think it's ever really going to be used against somebody.
No, I mean it feels more like it's research. It's cool. I love the idea of like the speculative type confusion. And just kind of the gadget they use there to use that to create a 64-bit pointer, despite kind of being limited to usually 32 access. Um, those are interesting things. Those are things they've definitely kind of pushed the field forward a little bit with those. At least as far as I'm aware, nobody else has really done that yet. So like there's some novelty here, but yeah, it's not the most practical or likely to be widespread, at least in my opinion. Somebody might come up with a really great attack utilizing it. More power to them, but at least with my simple mind, I don't see a lot of practical attacks here. Attacks, just some scary ones.
It'd be interesting to see this chained with an info leak in the browser. Um, because I think if you chained an info leak with this becomes a lot more useful. The problem is when you're talking about browser memory corruption, most of the time, if you can info leak, you can probably get code execution too, with the way bugs are in the browser. So a bug where you can only info leak, where you would need an attack like this, would be kind of rare, I think. But it would still be interesting to see, I think. And that is one case where this could be made more practical. So I guess I'll throw that in at the end there. Um, be a bit more charitable to the practicality of using this. But yeah, next we'll move into a post from JFrog Security Research on an integer overflow and HAPoxy, or HAPoxy, however you're supposed to say that. Or sorry, proxy. I was I was confusing it with something else. Okay, HAProxy. The issue
I
is in how
assume
it
the
deals.
HA should be set out because I think it's like high availability proxy. I'm not confident on that,
That would make sense
but
given that like the whole marketing angle of it is the high
yeah.
uptime and reliability. Yeah. So HAProxy we'll go with. The issue is in how they deal with header names and requests. When initially parsing a header or a header name, it gets stored as an HTX block internally, which consists of metadata like the header name length. And that header name length gets encoded into an 8-bit field, which leads to the obvious question, what happens if the header name exceeds 255 bytes in length? Well, there's an underflow because it'll wrap back around. So if you send like a header with a header name of 270 bytes, the name length is saved as 14. So it'll read 14 bytes when iterating over the HTX blocks, then read the value after that as the content length, which in their payload they set to 0. Um, in their exploit scenario, it gets read as the content length. So due to HTTP thinking it's already received the content length header, when it sees the actual content length header, it just ignores it. So it forwards a header with a content length of 0 to the backend with the way they structured their exploit, which then allows the next request on the same connection to be accepted as a legitimate HTTP request. And basically, it allows you to do HTTP request smuggling, which we've talked about before. It's just a very interesting way of getting there. Um, they
Yeah,
go
I
into
mean
detail.
the fact that we see a kind of binary level issue ultimately resulting in request smuggling, you might be able to come with something else here. Like some other sort of attacks. The main issue, I guess, or what you're able to do is there's kind of two stages to the processing. So one stage will read the content length and it'll think it's 60 or whatever the legitimate value is. And it'll think that content length, like the really long name, is some other header. And then it's the second stage that ends up seeing them both as being content lengths. Um, so you're kind of able to smuggle in an extra header into there, which you might be able to do something else with, but going for request smuggling seems like a really obvious route forward. Or
Yeah,
maybe
I mean, this
not.
basically is like a desync between stages. So
Yeah. Maybe it's not the most obvious thing. I don't want to downplay their creativity with this attack, but like going for the once you have something like that, I can't really think of any other attack. I also have the benefit of hindsight, but it does feel like, there might be something else you could manage that would be more application specific, like when it comes to the actual target or some of the rules that it's trying to pass.
yeah, they go into some detail about how they take advantage of the request smuggling, uh, or rather, how they get the response for their smuggled request, which is where they craft the malicious HTTP request, but they leave it unfinished. We've kind of seen that strategies before. I don't think there's anything super novel there. Um, but yeah, basically, this is a binary issue that leads to request smuggling, which is the cool aspect of it. Toward the end, they talk about how this could be automatically discovered by looking for a pattern where a variable is shifted, then added to. Um, that was also another thing I thought was interesting they put in there because um, not a lot of articles talk about how you could automatically find the bug with like a query or whatever. Um, they don't go into detail about how the vulnerability was fixed in the article, Though you can find it if you look at the source code. Basically, they just bail early and reject the header if its name exceeds 255 bits, or 255 bytes, or if the value length exceeds some like insane value. It's kind of funny though, because if you look at the original code, they have a comment in the function noting fix me, check name.len is less than 256. So they were aware that this was a possibility, but this was just another one of those fix me's that was just never addressed. It was just left in the source code and they never circled back to it. So,
So finding
um,
this automatically would be, grep fix me,
yeah, basically that's all you have to do
which is
to become a pro vulnerability hunter.
I mean, fix me was definitely in my set of regex that I'd run on a code review. Fix
Yep,
me's to do, bug, triple X, things like that would definitely flag my interest.
yep, definitely makes sense. Next, we have a Talos report on heap overflow and Ribbonsoft dxflib 3.17.0, which is a library used by various CAD tools to parse the DXF file format. I will admit I don't really do CAD design, so I'm not really familiar with the file format, but they do go into some of the background on that here. Mostly, it consists of like key and value pairs, or code and value pairs, as they call them. These pairs are used to define entities, which are usually denoted by a sequence of group codes, starting with a group code 0 and a value of LW polyline to mark the start. Then they rely on other codes being sent afterwards, being like code
So
90.
just to clarify there, the LW
Yep.
polyline is a specific type of entity. There
Yeah.
are a number of other entities that could be sent to. LW
Yeah.
polyline isn't always the start, but it is for a start of an LW polyline.
Yeah. For the purposes of this exploit, that's where they tunnel in on is the polyline entity. So yeah, when you send an LW polyline entity, it expects a code 90, which is supposed to be the max number of vertices that are expected, which will initialize an array of doubles for those vertices with a default value of 0.
It's
And
code
the
90 and
index,
then value 40. Or value 4, sorry.
yeah, um, and the index is set to -1 when you pass that code. It then expects the vertices themselves with the group codes of 10, 20, 30, and 42. Each of those having different behaviors. For example, if the group code is 10, it'll increment the vertex index. If it's 10, 20, or 30, it'll write those vertexes into the buffer, indexing using the group code divided by 10 minus 1 to write into the given slot for that index. The 42 code is a little bit special, though, because it'll always write at 3 spaces away from the vertex index. The problem is, it's expected that all of these code value pairs are sent together and in that order. So interesting behavior happens if you emit a code. Let's say you emit the 10 code, for example. Because if you never send a 10 code, the vertex index is assigned -1, which, when it gets to the 42 opcode, ends up indexing into the vertices array at 4 times -1 plus 3, which is -1. Obviously, that's going to be out of bounds of the array, and it ends up writing before um, that buffer in memory.
Yeah, well,
Um,
if that resolves down to, -1.
yeah,
Um, which is a very interesting out of bounds right to have. Um, it and exploiting that will be interesting, or could be interesting. They don't get into the exploitation here because this is a library. So the actual heap and like structure of any program is going to vary depending on the program it's loaded in.
yeah.
So they couldn't do that, but -1. So in something like ptmalloc, so the default C allocator, well glibc, I guess. I can't say default C. Um, that'll have metadata that's located just before the block that you can control. So this will write kind of in the 8 bytes for a double, the 8 bytes before the block. So that is enough to kind of mess with that heap metadata, and potentially compromise something. I'm just trying to think of a particular attack you'd be able to get here, given
So
you write the group value, so you do control what's being written there too. I'm not sure exactly what toReal does or how it's going to change the value. Sound like you were going to say something though, Spec?
yeah, so it's kind of interesting here because the vertex or the array you're writing into is an array of doubles. So you should be able to control like a fair bit amount of data. You could probably control like 8 bytes, for example. So if the metadata includes a pointer or something, you could smash that pointer. That said, you I don't think you could do like a partial overwrite. You would be overwriting all of the bytes. And that makes the exploitation scenario kind of tough because unless you have an info leak or something, you're going to be hard pressed to know what to write into that field to take advantage of it. Like, let's say you were doing like a heap on link attack or something like that. Um, you would need a valid pointer to stick in there of
Yeah,
what
I
you wanted to
mean,
target.
doing a modern like unlink attack would also require bypassing a number of other checks, which would require writing into other areas of memory too.
That's true. But
Because you'd
if we
have
just
to.
ignore that, like for the purpose of trying to
Oh,
be,
it's time travel.
favorable, yeah,
Yeah,
let's
no,
time
I mean,
travel back to like
it,
the 90s or something.
in trying to be favorable, there could be some stupid heap implementation too, because some CAD program decide they know better what the heap should look like and how it should divvy out things, and therefore send it out with some really weird heap structure.
Wouldn't be
I
the first
it
time a program's done that.
Oh, for sure not. Um, so there's definitely the potential for an attack here. The fact that it's -1 is just really interesting because of that heap aspect.
Yeah.
That is sometimes where you're going to run to metadata rather than just other heap data.
Now, this is kind of a naive question, but it is using so this is C++. It is using the new allocator and it's allocating an array of doubles. I don't know if C++ inserts anything like any interesting metadata
It it
into arrays allocated like that.
it still comes down to what allocator they're using. Um,
No, but what I'm saying is like if like I know new eventually does allocate from the heap using like libc or whatever, but does C++ add anything before the data you control? Does it like wrap an object around it? That's where I'm kind of
I
it's
don't
just
believe
something I
so.
thought of looking at the code. I don't think
As
so
far as I'm
either, but if
aware.
it does, that could be interesting too to look at.
Yeah, I mean,
Um,
really, just any sort of free memory space metadata is going to be interesting to look at here.
yeah,
And I guess just to toss in there, any basically any other vertex index, if you incremented a bunch or something, you're kind of limited, but you're basically going to mess with the writes into just another slot. You're going to have bad vertex write locations, but you're not going out of bounds. So this is the only one where you kind of end up out of bounds, which is why we're focusing it on this -1.
yeah. So in terms of exploitability, I think it could definitely be used. I think most likely though, you will need
You'll
um,
need more for sure.
you'll need an info leak most likely to take advantage of this. Does it zero the memory allocated? Somebody asked in chat. The double array is zeroed, but you're writing out of bounds of the array. So whatever is there in memory beforehand will be whatever it was set to. Um, but the array is zeroed, if that's what you were asking. So yeah, exploitability probably could be with another issue, but like you said, Talos just doesn't really go into detail on that. It is a library here, so it is dependent on the target, but in general, Talos just doesn't really go into how an issue can be taken advantage of. They just kind of show how it's an issue and then end it off there. So yeah, we do have one more topic left for this episode, which is a ZDI post on Parallels Desktop. This is a stat clash vulnerability, which is kind of interesting. It's not something you really see too often. Parallels, for those not familiar, it is a macOS virtualization app. Specifically, in this blog post, they look at the request handlers and the toolgate protocol for host and guest communication. One of the API functions that's provided for handlers to use is this TG get buffer function and TG read and write buffer functions to copy from and write to guest memory, I believe. The vulnerability they found is some places would call this function with an unrestricted size, which is a problem because it would copy the data onto the stack in the hypervisor. And the way the stack works is threads will get their own stack in a region of memory. And a stack clash can happen when one thread can write into the stack of another thread, right? Because they're all just laid out linearly in memory.
Yeah, so
Um,
Stack Clash, like in general, as a vulnerability class, is just pointing the stack outside of its own memory region.
yeah,
Just as the general attack. In this case, it is kind of going to another stack. Where you have one thread stack incremented enough to go elsewhere, which we kind of covered at once before, actually, with that GPU vulnerability, I think it was, where you'd increment the stack onto another GPU's thread. But
I
let's
feel
keep
like
going
you're
with
you're
this
ringing
one.
a bell, but I can't remember exactly what that was. But yeah. Now there are guard pages in place to try to crash the program in an event of a stack clash to prevent it being taken advantage of by an attacker. Those pages can be jumped over though using various tricks like abusing functions that allocate on the stack but don't actually use that memory. Because the way that the guard pages work is you have to actually like write to or read from that memory in order to trigger it. So if you can just get like an empty allocation, you could leap the guard page, which I believe is what they do. Um, they speculate, and there's also some mitigations in place, by the way, that should be able to prevent stack clashing. Clang, like Apple's Clang, has a mitigation against it where it'll instrument stack allocations and validate the size, and it'll safely crash if it would cross into or past a guard page. Um, What's weird though is Parallels Desktop didn't have this instrumented code put in place that Clang's mitigation would put in there, which is weird. It means the mitigation was disabled in some way. They speculate on why that could be the case, wondering if maybe they just disabled the mitigation outright for some reason, or if they use some other option to the compiler, like the Mac OS X version min, which would silently disable that mitigation. I could see it being the case where they would disable it outright, possibly because of performance overhead. I'm not sure what the overhead would be on like a stack clash mitigation. I don't imagine it would be super high, but when you're talking about virtualization,
Yeah, I'm
it does become
actually
a concern.
I'm going to lean towards the accidental side of this one. I mean, yeah, it's possible they disabled it, and we don't know for sure, but the accidental side being just that, um, that was when they tried to basically make it backwards compatible. Uh, by default, that mitigation's turned off, and they just weren't aware of it. That's something I could completely see somebody just not being aware of, overlooking. That's something I could see myself not being aware of and overlooking.
That seems the more likely of the two speculations that they have there. But just to highlight, like just to hammer the point home, that is speculation. Parallels isn't going to comment on why that mitigation wasn't there. Um, But yeah, so there's two things in this post that we don't really see on the podcast often at all, which is the stat clash vulnerability, as well as what they go into detail in the end, which is using binary ninja for variant analysis. We have seen variant analysis done before with things like CodeQL and whatnot, um, but I don't think we've seen Binja brought up in that context, as far as I can remember.
I think we've seen
So
it
that was the other
once.
half of the post that was cool. You think
Yeah,
you've
they
seen it before?
don't. I think we've seen it once. I'd have to look through my notes to find it. I don't think it was ever brought up in any detail. This is even more detailed than the last time I think it was mentioned. But at that, like, it's not a super detailed look at using Binja. Just the fact they used Binja's API defined. Um, what was it? Effectively where.
I think they use their static API to check what the possible register values would be around dynamic stack allocations, and they would check those possible register values to see if they would go past your own stack, basically.
Well, so no,
Um,
what they were checking was after the TG read buffer. They basically checked to see if the RSP value was undetermined. That was one of the main
oh,
things
right,
they
okay.
were looking at, was just if it became undetermined or undeterminable for the static analysis to know how large RSP was. It was likely that TG read buffer was writing onto the stack, or something was writing onto the stack with a undetermined size. So that's what they did. Kind of a naive approach to it. Would only really find, if they're looking at with TG buffer call and then RSP, only would really find those cases. But I mean, they did find a couple other cases with it. So I mean, it works.
Yep, they found two other vulnerabilities of the same issue. They found it also in the original one. They found it in TG request inv sharing, and I think they also found it in TG request GL create context and TG request direct 3D create context. So like graphics type stuff, which doesn't surprise me too much. But anyway, yeah, this is an interesting attack, and I've always kind of said it whenever we have virtualization topics, but whenever you're talking about a target that's like a virtualization platform or whatever, it's immediately one of the most interesting targets you can look at. So, yeah, we weren't going to let this one slip through this week's episode.
Yeah, and I mean, honestly, with some of the episodes, I want to get into some virtualization attacks myself, specifically Hyper-V, but just in general. And the more we keep covering various hypervisor issues, the more often I feel like it's a lot more accessible, and there are still some low-hanging bugs around, although that does tend to be in VMware's products. At least
Yeah,
from what we've seen. I mean, I haven't seen a lot of write-ups for Hyper-V. I guess there have been a couple, but like we've seen things like double fetch, which you just don't see in like kernel like on Linux anymore. But you'll see that in like hypercall implementation in hypercall handlers. So I mean, some of those older vulns are kind of still there, still around. I guess you do still see it on like Windows drivers, but Windows has its own challenges.
yeah, VMs from a security standpoint are kind of where operating systems were like maybe like 10 to 15 years ago, is how I'd put it. Um, they're very complex pieces of software, and they're relatively new compared to kernels, like the common ones that you see, like Linux, for example, and BSD. So it's just a good target to look at because of how complex it is to deal with.
But not
Um,
as much information is available about their internals. Not as readily understood. There's
yeah,
definitely a
especially
barrier to
something like
entry.
Hyper-V. Yeah, but yeah, that covers all the topics that we've had for this episode. Thank you to everyone who tuned in. You can catch the VOD on Twitch or on YouTube at 8 p.m. Eastern on Wednesday. We also have previous podcasts up on Spotify, Apple Podcast, and more links on Anchor. Feel free to join our Discord and follow us on Twitter. Links for those of you who want to check them out are below the video and the description. I'll also put them in chat. Um, but yeah, with that said, we'll be back next Monday for our bounty episode at 3 p.m. Eastern, 12 p.m. Pacific, and next Tuesday for the binary episode at 7 p.m. Eastern, 4 p.m. Pacific. And we will see you all then.